All right, welcome back, everyone. Today we're going to be talking about optimization. Currently, we built our training model. Just to do a quick summary of everything that's going. First, I'm going to do a visual summary, and then after that, I'll go ahead and go into the actual code of what's happening. So if I were to start off explaining our model or our process, I'm going to go ahead and start off with our data file. We grabbed our data file, which had pure data. We looked at that pure data and identified that there may be some skewed values or that they may be an absence of data. So we needed to standardize and scale our data. And we did that utilizing sklearn. We utilize sklearn and pandas to fill in any sort of missing data. And we utilize sklearn to actually scale and standardize our data, right? Make it all fit between that left and right lateral limit so that we have a good stream of data being fed into our model. We then grabbed our clean data file, again, utilizing sklearn. We fed that clean data into a batch, or we separated it into a training batch where we had training data of the size of 80% and testing data of the size of 20% to ensure that our model isn't learning the data, but it's actually learning the patterns and connections in order to make accurate predictions. We then took this data that we had cleaned up and fed it into a data loader. Now, that data loader accepts data sets, and those data sets would have to be built from tensors. So we built a tensor data set, and I see that right there says data sets. So we'll go ahead and add tensor data set. We built a tensor data set that took in this batch of training data and testing data. So we have two of them, two data loaders, one for testing and one for training. Where the data loader would grab a randomized set of 32 samples out of the tensor data set, right? And then that randomized set would get provided into my training loop, which if I were to zoom out a little bit here, we can see the training loop where my data makes an estimate, and then my loss feeds back the update of weights and biases to each one of my linear layers, right? So it gets fed, goes through my model, my output then comes out, at which point we decide, hey, I want to conduct some sort of back propagation to update each one of my layers, weights, and biases. Well, I do that by calculating my loss, right? And along with our loss, we have an optimizer that helps our loss and our model be able to find the optimal minimum in order to actually make good and correct updates to each individual layer. So here on the left-hand side, we have the loss breakdown that we shouldn't expect just a direct drop the entire time. We should see something that kind of squiggles or may plateau at some point, may spike back up. But if we zoom out, we see that it's actually, in fact, dropping, right? It's just doing it in a much slower and inconsistent way, but the overall pattern is, in fact, dropping. We then talked about our optimizers and the different types of optimizers that we could use, such as SGD, where we would have to specify the learning rate and momentum. And then we talked about Atom, which is a more adaptive optimizer that pretty much in itself takes the default values of 0.01. And once it takes the default value, it just pretty much learns on its own, right? It takes a step, takes a look at what the terrain or what the parabola may look around it, and it determines whether it needs to build more momentum on its own or whether it needs to adjust the learning rate, which is the size of the step that it's taking on its own, which is really great because now we're not trying to run this SGD or trying to plot it and try to do some weird linear algebra to try to figure out how to actually get there, right? So there's our entire training loop in concept, right? Does anyone have any questions over what we've done up to this point? Okay, it doesn't seem like there are any questions. So let's start looking at some code. Again, we start off with our data. We grab the pure data file. We fill any of the null values here with data dot fill null, and we fill it in with the mean of each column. We then grab all of our features. We drop the probability to ensure we have our features separated from our target. We then grab that information and split it into the training split that gives us our 80 to 20% batches. And then we make those into scalar data, right? We make sure that our data is actually scaled and standardized. So now we have clean data, clean features that have been scaled. We turn them into tensors because that's what we're working with here, our tensors. And we grab those tensors and feed them straight into some tensor data sets. And then we feed those same tensor data sets into data loaders, which gives me a training loader and a test loader. So up to this point, I've gone through the entire bottom process of working with my data. I cleaned it up, and then I fed it into two separate data loaders. Right? I then build my model, which takes in a first linear tensor of 9. So I'm expecting 9 features from my data. And I slowly funnel down all the way to output one single feature that gets squeezed within the sigmoid function so that we have an answer between 0 and 1. I then utilize the forward pass to pass information forward, and I create an instance of my model. Then we go into the training loop. Currently, my training loop is of 2,000 epochs. I'm utilizing Atom and the parabola that it's iterating through to try and find the optimal minimum comes from my model parameters, right? The criterion that I'm utilizing to figure out the loss is binary cross entropy loss. And then finally, I'm iterating through the number of epochs. Within each epoch, I'm iterating through all 32 batches that the training loader will give me, right? And for every batch of those 32 batches, I am actually feeding it through my model, taking the output and comparing it to its actual true result, which we reference to as the label, and then apply the back propagation step. This is where weights and biases are being consistently updated, starting from the last neuron in the neural network, moving backwards to the very first 9 neurons in the neural network. Okay. And then finally, I evaluate. The evaluation looks almost exactly the same as my testing data, but I'm actually, or excuse me, as my training data, with the exception that I'm not within a nested for loop epochs. I'm just grabbing 32 out of the test loader at random, iterating through those 32 batches, and out of those 32, excuse me, iterated through those 32 samples, and out of those 32 samples, computing an accuracy score, which currently am at 0.62, which isn't bad for the very first model. All right, my loss looks like it goes all the way to 0.70 in the last print statement. But if my accuracy is of 0.62, I'm assuming that my actual loss is a lot lower than 0.7, right? It's likely somewhere around the 0.5s. It's just hidden between those print statements. All right. And there's a general review, both in concept and of actual code. At this point, does anyone have any questions over everything that we've covered up to this point regarding deep learning with PyTorch? All right, let's hear, Brandon.
So because we're claiming that this is a learning model, I must have missed it, but where is the knowledge get stored? So like we have our data and we're training on that data, but where does that knowledge or learning uh persist?
Yeah, that's a great question. And I guess for us as people, it's a little bit hard to picture, right? Because my idea is that somewhere there would be some sort of, not necessarily a dictionary, but some sort of data set or something that my model can refer back to and say, oh, well, this is going to cause this information, right? At least when I study or I'm learning, I know that in my head, I have a bunch of pictures over different concepts and knowledge, right? Like if I think about React, all I see is a bunch of boxes inside of boxes and how they are connected to one another as far as components and pages. Now, inside of my neural network, the part that's considered learning or retention, I guess, where our model is actually learning and adapting, is within our weights and biases. So every time our weights and biases are being updated to have new values, which happens in the back propagation step or the backward step, um, that's the model learning, right? It gave a incorrect result. So we're going back to each neuron of this model and updating the weights and biases. And that's how my model essentially learns. So as far as where the knowledge is being stored, it's being stored at each individual linear layer with its according weights and biases. Does
So
that
we're
answer your
re
question?
so
Oh,
we're
go ahead.
just to be clear, we're reassigning the values to a new value every iteration or every epoch.
Not every epoch. We're assigning it every single time the backward step is being applied, which is after we go through every sample that comes out of the training loader, right? So for each epoch, I'm updating these weights and biases 32 times. So if I'm doing 2000 epochs, right? I'm not gonna try to do this in my head.
No,
Actually, that should be
okay.
pretty soon. It
I'm
should
following
be
along.
64. Yeah, 64,000. Sorry. Go ahead.
So where is backward coming from? Backward is a function of what particular framework that we're working with? Is that PyTorch specifically?
Yeah. So the
Okay.
backward step is actually applied in any of the learning models. A lot of the language that you'll see here, or excuse me, learning languages, a lot of the language that you'll see here is common across other platforms like TensorFlow. Uh, the backward step or the backward method is a method that belongs to the BCE loss class. So the
Oh,
class itself gives us access to that method.
okay.
Awesome. All right. Any other questions? Okay, great. Well, now that we're up to speed as to what our model is doing, what it looks like, and how our training is happening as far as back propagation goes, or the backward step, and how we're computing our level of accuracy. Today, we're going to start talking about how we can actually improve this model, right? As of right now, my model can only guess or make the correct prediction 62% of the time, which isn't very impressive. Yeah, it's already a true or false expectation. So I would at least expect it to be right 50% of the time, right? So 12 extra percent isn't really much of a change. Now I say it's not really impressive, but if we really think about it, like think about how easily we passed in just a series of data, right? We passed it into neural network, and someone already did all of the math, all of the connections that need to happen behind the hood or under the hood, right? Behind the scenes for us, for my neural network to actually feed this data and update each individual neuron. Now, it's actually it's pretty cool, especially the fact that somebody made it into a framework that's so easily utilized by everybody. That's very impressive. So now let's go into optimizing our model. All right. What kind of techniques can we utilize to optimize our model? And the first thing that I'm going to be covering here is going to be the order of your function. So far, what we've seen up above is pretty much a triangle shape, right? Let me go ahead and put that here. I have this triangle funnel that is feeding or taking in my tensors, feeding it through the neural network, and then trying to learn or adjust it by doing a clear descent. Now let's take a look at the number of connections here, right? Let me make sure that this graph is in fact correct. It is not. There you go. So that's more like it, all right? We can see that our neural network is fully connected. Each layer is speaking to the next one, and eventually spitting out a number between 0 and 1. But look at the connections here. They're very limited, right? We're not giving our model the ability to maybe try to understand a more in-depth pattern as to what is being fed into the neural network. And we're not really giving it much room to make connections and adjustments, right? In total of weights and biases, there's not that many. Let's see, that's 3 by 2, so that's 6, 2 by 1, that's 2. So weights, we have a total of 8, and then biases, we have a total of 5, right? So there's not that many connections happening here to allow my model to learn more effectively or more efficiently. I did say that 3 linear layers is typically more than sufficient to do this, but maybe the way we're going about making our connections isn't the best way, right? Let's go ahead and break this down a little bit. So here's my image where I have 9 neurons, and I'm going to put it this way so that I'm not consistently highlighting everything over and over again. I'm going to feed those 9 neurons, or as we see in tensors, into the neural network. Right? So it goes into the neural network. Rather than funneling it strictly down, well, I know the final aspect that I want is going to be of one individual neuron. But now let's try to stretch the neural network like this. Rather than just strictly funneling it, let's first open it up, right? And by opening it up, I am now allowing my model to have a more capabilities to make better assumptions and connections, because now it's seeing some it's going to be able to create better patterns in between each layer. All right. So we open it up, and then from there, maybe we don't want to collapse it all the way. We could still grab one layer at a time. All right. Bring it back. Now it's back to 9. We bring it down to either 6 or 8, whatever works for us. So in this case, it looks like 6 might be the magic number. Right? And we get the picture. We're essentially just opening up our neural network so that we can allow for more of these connections to be happening. I could draw out each individual line But essentially what's happening here is this one neuron would now be connected to all of the neurons on the other side. All right, so mathematically speaking, if I were to take a look at layer 1, which let's say takes in a total of 9 layers, but spits out 15, well, that means that in weights, what I have is 9 times 15, which I'm not going to try to do the math for because I'm probably going to get it wrong. And then as far as in biases, or biases, which is the easy part, I have the next layer, I have a total of 30. Right? So there you go. I have my third of biases because there's 2 biases being applied per each individual neuron. So there's 30. And then I have my weights where it's 9 times 15, which 150 minus 15, I'm assuming is 135. I'm pretty sure. Excuse my math if it's wrong. Right? So now I just changed it to where if I was funneling down, like the way I have it here, where I have 9 and 7, well, in between 9 and 7, I only had, and let me do it this way. Let's go into layer 2, where layer 2 had 9 and 7. Well, in layer 2, I only had a total of 63 weights, and my biases were a total of 14. Right? So there's my issue. I don't necessarily have the amount of connections that I need in order for my model to learn properly. Does anyone have any questions regarding why we would want to, rather than have a strict funnel where we have a triangle, we would want to open up the connections and then narrow it back down? I see a question from Momo. Go ahead.
Yeah, just I want to know, how did you calculate the biases the first time? 30.
The biases.
Yes.
There's 2 biases per output neuron. So you just take the output that you want and you multiply it times 2.
Okay, thank you.
Of course. All right. So let's go into applying this into our model, right? I have my 9, my 7, my 7 and 4, but that's not necessarily what I want. Instead, I want to double it, right? And that's going to put me around 18. So just to make things easier for me, I'm going to make it to where it's 20 neurons. I'm going to then utilize 3/3 to bring that down to 15 and output 10. This 10 will then output 5. And then I could add an extra layer here where it would take in 5 and output 1, right? And this whole 3/3 thing isn't really like a standard. It's just something that when I experiment with neural networks, I found out that it works for me really well. By opening this up, well, now I have way more connections happening between my binary model, right? Each layer has now grown considerably as far as the connections in weights and biases that it's able to make. So now that I've updated my linear layers, what's the next thing that I need to update in my model before I can start training it? Let's hear it, Momo. If you're speaking, you're muted.
Yeah, I think next now we're gonna define again the loss function and the optimization.
Yeah, that's close, right? We're not actually going to change our optimizer or loss function. These 2 would remain the same, right? Atom is already adaptive, so we don't need to necessarily change the learning rate. and it's already taken in my model parameters, so it will update on its own. And the binary cross entropy loss, that's the standard as to what should be utilized for binary classification models. Instead, what I would like everybody to think about is we've made these layers or these attributes, but we never once changed our forward pass of how information is being fed into our neural network. Right? We have this linear 1 all the way up to linear 3, but we are currently missing our new additional layer of linear 4, which then gets fed into the sigmoid function. All right. Well, let's try to see if that changes anything. So currently, the last loss that I had here, I'm actually gonna copy and paste it here so that we have it on record. And I'm gonna change this to 1,000. So this may not be very effective as far as showing us the change in accuracy, but hopefully we can still see it. I'm cutting the number of training in half. That's for time consistency. I don't want to have everybody sitting here just watching this model being trained. So let me go ahead and restart this. I restarted the kernel. There's nothing saved in memory space. Nothing has been executed, right? I could clear all outputs so that the outputs are no longer there. I'm going to execute each block of code. So here's the first block of code that has been executed. My model was created and my data was made. My second block of code seems to have ran into some issues here. Let's see. Mat1 and Mat2 shapes cannot be applied to 16 by 20 and 15 by 20. Output is truncated. View is scrollable. Okay, so at some point we're outputting 16 and then we're trying to push it into a 15 by 20. So I messed up something in my layers here. Here you go. So I have 9 and 20. Then I pass it down to 15 and 10, right? Well, we know that I want 20 and 15, and I want 15, and I'm gonna make this 8 because I don't necessarily want to cut. I'm gonna cut this down a little bit more. I apologize, everybody. And I'll go from 8 to 1 to try to make this a little bit more efficient, right? So I go from 9 to 20, feed it from 20 to 13, 13 to 8, and then those last 8 neurons will then output 1. So let me restart this one more time. And let me clear all outputs and execute it. There you go, our model was created. Our training process is now working. So right off the bat, I already had a 0.66 loss. We're at 7.2 now after 100 epochs. And we're going to see this kind of bounce back and forth. We could create something that will keep track of what the minimum loss was and when it happened. We'll add that here shortly. We should see it stabilize and then slowly drop here. In the meantime, while this is training, I see Erica has shared a Geeks for Geeks. Yeah. And it talks about backpropagation in neural networks. All right. So 500, 600, almost there. We may have to keep a shorter number of epochs for class. Otherwise, we're going to sit here watching our training model for a considerable amount of time. All right. There should be one more print statement. Okay, great. We shouldn't see any more. The next thing that we should see is our accuracy being printed out. And there you go. So we're at 628. Now, this may not look, oh, wow, it's almost exactly the same. Now, this may not look like it is exactly the same. This may not look like a huge difference, and especially since You know, we got the same exact accuracy. I wonder if our loss, no, our loss was different. Um, but keep in mind that I am only training it half of the time that I was training my model before. All right. So with half the amount of training, just by changing the structure of my neural network or how I'm feeding these neurons through the forward pass, I already made my model that much more efficient. I was able to get the same result with half the amount of training. All right. At this point, does anyone have any questions over why we would open up our neural network before closing it back up? Let's hear it, Mama.
Yeah, just the criteria of feeding the neuron. Do we have any criteria for feeding the neuron? Like we start with 9 and then 920, okay?
Mm-hmm.
And 2013, the input and the first input.
Yeah, so these should connect to one another, right? So that 20 should be the same thing on the next layer. So if I made this into 15, and this would have to reflect the 15. If I made this into 10, this would have to reflect 10, right? And actually, let's add another layer here. Let's do
I just
5.
meant, yeah, when we feed this layer with any number of neurons, is there any character, like you start with numbers and then it didn't work, so you change it. You start with number of neurons and it didn't work, so you back and change it to 9, 20, 20, you know what I mean? So do we have like something based on this thing we know how to feed our neurons or our neural network, the number of neurons that we
Yes.
use?
So the first number of neurons should always match the data that you have or the amount of features that you're passing into it. From there, I'm
Yes,
essentially just doubling it. And then after that, everything down
that's it. Yeah,
to the last
yeah,
part really doesn't apply, right? Like you can make these whatever numbers you would like. They just have to reflect where the last output of one layer
yeah,
is the input of the next layer.
yeah,
Okay,
yeah. That's what I was asking about. Yeah, thank you.
of
So
course.
just double the number of features, right? That's it.
Right. Yeah, that's what I
Okay,
did.
thank you. Yeah, thank
Of
you.
course. All right. So now I'm just going to go ahead and add that last layer here. And for demonstrational purposes, we're going to be working with 100 epochs moving forward, just because we do not have the time to watch this training model go through the entire process. So let me go ahead and change this to 10 so that we can see it every time. Go ahead, Momo.
Yeah, I have another question. Is there a limit for adding this extra layers? For I mean, for the optimization process, we just add more layers, right? So is there a limit for adding this layer? So
No.
because yesterday you were talking about the overtraining.
Yes, I did talk about overtraining. You could add as many layers as you would like. You don't necessarily want too many because it's just going to take more performance and computing power for your model to actually come up with an answer.
Uh-huh.
Um, but we're not, this doesn't necessarily touch the topic of overfitting just yet. Does that
Okay,
answer
so
your
is
question?
there like, yeah, is there like function or something based on it? I will know this number of layers will be suitable for this model,
No,
for this number, nothing? Okay,
no,
yeah, thank you.
of course. All right. So now we did it for just 100. We changed our neural network a little bit, and we look like we still have the same level of accuracy. Oh, no, there's a little bit of change, right? So there we go. Now we have 4.8. Oh, no, that we don't. 77580261 Yeah, we still have the same exact level of accuracy. Okay, awesome. So there's our model. It's been trained. We're able to update it, and we're able to get a little bit of a better result with less number of epochs. Good. Well, now how do we make this even more efficient, right? Because we still don't have it guessing the way we wanted to. Only a 62.8. If I run this through maybe thousands of epochs, we could improve that. But likely the ratio is going to be very small. Maybe for every 1,000 epochs, we'll improve it 0.001. And that's not necessarily what we want, right? There's got to be a more efficient way to do this. Well, let's think about what's getting fed into the neural networks, right? Sometimes what gets fed into the neural networks isn't necessarily an output that we would want to reflect on each layer, right? Think about the impact of negative numbers, right? What if I had something that was negative 0.02 being applied from one neuron to the next layer, right? Because this one negative 0.02 or negative 0.2 would be applied to the entire neural network, right? Because we're fully connected. Well, negative numbers don't necessarily provide good outcomes or good values for a neural network. So we need a way to tell our neural network, hey, we don't want to consider these negative numbers, or we need to have a way to handle these negative numbers where as our neurons or our neural network is feeding each one of these neurons, if it identifies, hey, on the next layer, this number currently right now is 0.03, right? And it might turn into a negative number. Well, we need a way to bump this so that it never reaches this bound or this limit of 0, right? So how could we do that? Go ahead, Momo.
I think we need to change the activation function, the sigmoid.
Yeah, that's a great question. We do have something like sigmoid, right? Where sigmoid would essentially just put everything in between 0 and 1. And at this point, we are talking about bringing in an activation function, right? I'm no longer just feeding neural networks or just feeding each layer. I am trying to add some sort of activation to each layer to ensure that each layer is outputting the correct values. All right, so I'm going to go ahead and make a copy paste of this, bring it over. And this is starting to get a little messy. I apologize, everybody, but it is the nature of the beast. All right, I'm trying to nest my linear layers inside activation layers that ensure that these linear layers are trying to avoid negative numbers altogether, right? Or something that wouldn't be productive to the neural network. Well, what this activation layer would be called is Relu. I want to apply Relu to each layer to ensure that my model is actually learning with correct input and that it's able to dump or bump input in the correct direction. Right? Well, how do I do that? How could I apply Relu here? We're actually going to import something called, it's going to come from NN. So I'm going to say from torch.nn. And this is called functional. I want to import functional. I'm going to import it as capital F, right? That's just an alias so that I don't have to write functional every single time. Well, I have this functional class, but how do I utilize the methods within it? We talked about applying these activation layers. So all I need to do is grab these linear layers. I'm going to wrap them inside a function call. Then I'm going to say, hey, from functional, I want to utilize Relu. All right, so there we can see the Relu function being applied. It's taking the output of my first linear layer, right? So it gets fed through my neural network. My neural network spits out 2, and then my Relu grabs the 2 neurons that have been spit out and fixes them, bumps them so that we have the correct output. Well, let's see what our neural network looks like now. I'm going to take my loss here, which currently it's at 0.669. I'm going to take my accuracy, which is actually exactly the same, so I'm not going to change it. 0.26112. I am now going to go through the process of, again, restarting my kernel to ensure none of this is saved. None of my weights and biases are saved. I'm going to clear all my outputs. I'm going to run it all again. Let's make sure it works. Okay, my model was fed. I'm going through my loss function. My loss function seems to this time have dropped down to the force. Consistently in the force. At one point, it even reached 0.27 for my loss. And my accuracy has now increased. I now have 6.4 instead of 6.2. So my model is just that much more accurate now. I'm 64% accurate. I've raised my accuracy by 2%. Not a huge leap, but it's definitely a good starting point, right? Now keep in mind this accuracy has improved from only 100 epochs, right? Which, yes, we are iterating through 32 batches every time. So technically it would be 3,200 loops that we just put our model through. But that's still not a lot of loops yet. And our model has become pretty accurate. Well, the next thing that we're going to talk about, which is a method to try to prevent overfitting, is going to be the dropout function. And actually, before I go into that, does anyone have any questions regarding Relu, how to apply Relu, or why we're applying Relu? Let's hear it, Brandon.
Why did you use F-Relu instead of NN-Relu?
Yeah, great question. So as far as why I utilize function Relu instead of NN Relu, you could call it straight from the NN module, just like Brandon asked, where I'm calling the class itself. This is purely a syntactical preference. It is the functionality is still the same. NN Relu is running the same exact logic that functional Relu is doing. But by grabbing functional, I now have access to all of the different functional layers, and I don't have to make an instance of the class. Whereas in NN Relu, I would have to make an instance first. So inst of Relu. And after creating the instance, then I could pass it into a value. I would have to say inst of Relu and pass in a layer, right? I have to make the instance of the class first before actually being able to utilize it. Whereas in functional Relu, I could utilize it without creating the instance because it is a function and not a class. Does that answer your question, Brian?
Yeah, but is one preferred in production, or is it like you said, it's like syntactical, like preference?
Syntactical preference.
Okay.
All right. So now there you go. I have my functional Relu is being applied, right? I never had to create an instance of Relu itself. Well, how about I think about my model again, right? I go back to my model. How does my model determine this information, right? Well, if we think about our model and the way this dynamic is being built, likely the neurons in the middle of my model will have the most connection and the most impact as to what my model is going to output, right? So with that said, how do I ensure that my model knows, hey, we need to be able to identify, hey, if we're relying too much on specific neurons, and we need to have some sort of rate where every time we train the model, each layer should drop this random number of neurons and not utilize them for the training. So what I'm trying to say is we feed 9 neurons into our model, right? And 20 neurons, there's not actually 20 here, but a number of neurons get outputted, right? Well, all my dropout function is going to do is at random, it's going to, hey, we're not going to utilize that neuron, this one, or this one during this training process. All right, so it doesn't utilize any of those neurons. Just at random, it cuts it down by 50%. All right. On the next iteration, well, at random, again, this is a new sample or a new batch size that we're going through. We're going through a new 32 batches. Well, in this iteration, I don't want you to utilize this, or this. Right? Only those 3 neurons are not going to be utilized, or those 50% of these neurons are not going to be utilized. And it continues that pattern so that every time my model is attempting to learn and make connections, it's not doing it where it's over-relying on specific neurons. Now, what is that allowing for my model to do? Well, now my model is going to be able to make better connections because it's not always going to have the same exact pattern, right? We're throwing in some sort of fluidity to our model. Rather than having my model work in a straight line, as we've seen before, right? I am telling my model, hey, you are no longer going to work in a straight line because now not only are the neurons being mutated because I'm throwing in the Relu function, I am also telling you oh man, my TL draw skills are not working out today. I am also telling you that there are some neurons that you're not going to use and some that you will. All right, so rather than my model just working in a straight line from point A to point B, taking an input and providing an output, it is now taking an input. As it's feeding it through the neural network, it's making sure that that input fits a parameters thanks to the Relu function. And then I'm also making it so that it's not using all of its neurons every single time, forcing it to make better connections between each individual layer of neurons. All right. So I'm making it more fluid rather than just being a straight arrow. Well, now let's apply the dropout function, right? Where randomly, I'm going to drop half of my neurons. What would this look like? I'm going to go ahead and, after every linear layer, make an instance of dropout. So I'm going to say self.dropout1. And I'm going to make this dropout. And dropout just takes in a parameter. It's saying, hey, well, what percentage of neurons is it that you want me to drop every time? The typical standard is 0.5. It works really well. I don't necessarily see a reason as to why you would want to have something different. And I definitely do not recommend it. Right, so after each linear layer, I'm going to apply the dropout function, with the exception of the last one that actually provides my final output. Now, this one here should never get dropped because that's my last layer, right? My last layer that actually provides my one final neuron that I'm applying the sigmoid activation function to. So I need to make sure those 5 neurons are always being utilized to create my output. There should never be a dropout function for the last linear layer. So now how do I apply this? right? I could make it where X is equal dropout, or excuse me, self dot dropout 1, and then pass in X, right? But instead, I'm going to write this a little bit more officially. I'm going to pass in self dot dropout 1, and it will drop the following. Right? Now apply this for the other 3 layers. I'll say self dot dp. And then finally, I know that I want dropout 2, dropout 3, and dropout 4 to be applied. There's not a dropout for my last layer of linear 5. And you can see self.linear5 is being called within the sigmoid function. Right? Everything is still being chained. I'm still dropping out the number of layers. The only thing that's growing is the attributes within my model. All right. Now, before I open up for questions, let's take a look at the changes here. Here's my final print statement for my epochs. And here's my accuracy. That did not copy correctly. Try that again. Oh no, yes it did. No, it didn't. There you go. So let me restart my kernel one more time. That means all the memory is being dumped, right? As of right now, none of this exists. And I'm going to recreate my entire model. All right, we can see it going to the neural network. There we go. We're at 0.53. And there's a little bit more of a consistent drop now, with the exception of that. All right, and now let's see how our accuracy. Oh, hello. What is going on here? Did I copy and paste something too many times? Yes, I did. Interesting. Let's see here. Excuse me, everyone. It looks like I messed something up here. Okay, there's my accuracy. There's my epochs. All right, let me restart and send it. Okay, that executed properly. It's going through the epochs. All right, it finished with 0.64. And now my accuracy has increased from 64%. All right, we started at 62 after readjusting our linear layers and applying the Relu function. We had 64. And now by applying a dropout rate, we are all the way up to 68%. This is great. All right, almost at 70%. And this is only after 100 epochs. So my model is performing really well, and it's becoming a lot more accurate by just applying a couple of simple functions into my training model. All right. I made some nonlinearity connections between my neural network to ensure that it's able to learn correctly, and it's not just memorizing data. All right. I'm going to save part 2, which is going to be the implementation of how we would have a validation loss or how we would apply early stopping to the training loop. But as of now, I want to open up for questions. Ask the dropout function and the Relu function. How are they applied and why we have them? Let's hear it, Momo.
Yeah, so the Relu function is just taking care of the negative values in the data.
Negative and 0 values. It's trying to bump those
And
so
zero.
that they're not present.
Okay, so negative and 0 values.
Yes.
Okay, thank you. And is there any criteria to apply all this optimization function? Like we apply 3 things now. We dropped some neurons, we applied the Relu, and we in the beginning we did something else. We we changed the number of neurons. We changed the neuron network shape. So every time I'm gonna make my model and learn it, I have to apply all this things to make more optimization.
Yes,
Or
this is for optimization purposes, right? So what we went over for the last couple of days was the very minimum standard as to how you could create a
okay.
neural network. Now we're just optimizing it.
So every time I will design my my learning language, I have to apply all this or make it more optimized as much as I can.
Right. This is to make it more optimized. You do not have to apply it, but it is very much encouraged.
Yeah, it's gonna be better. Yeah, thank you.
Of course. All right. And I think Gary, you had a question as well. I'm not sure if your question was answered.
Uh, I had a conceptual thing. So the big portion of this is the weights and biases of each neuron. It's like each neuron starts with a random weight bias. You go through, you change what that weight bias is over time. And then when you do a dropout or a Relu, you're essentially adjusting or removing a specific neuron's weight and bias. So that way, when you go to calculating like a forward pass or you go through a backward pass, it's not the same weight that's being applied to the output. Am I understanding that correctly?
Yeah, you definitely are, right? So if I were to think about the training loop and how this is being applied, right? I'm dropping specific neurons, not for necessarily or excuse me, for updating purposes, but for better neural connections, right? So if I were to put this, and this is at random, obviously there would be more neurons that are getting killed, because we're utilizing 50%. But essentially once my model goes through this connection, all right, the first layer is still going to connect to all of these. All right, and let me do it this way. Yeah, the first layer is still going to have a direct connection to all of the neurons up above. Right. When it goes to the second layer, it no longer has that connection. So these two are being connected, right? But this one here, it's not being allowed to have any connections. It's being contained. All right, and it's moving forward. All right. Again, this one's not allowed to speak, so it's being contained. Then the next one moves forward, and so on, right? All the way into the next layer. Now, by doing this, when I do the back propagation step, these weights and biases, even though they didn't interact with the next level, they are still being adjusted when I take the backward step, right? I'm still updating these weights and biases. And although we may think, oh, well, that doesn't make sense, right? We're not using them, or are we updating them? It works in the fact that we're creating this nonlinearity to our models' capability of learning and the connections that we have, right? So that they can make better predictions. So those, even though they're not being utilized, they're all the math to figure out how they could be adjusted to actually improve the neural network is being done under the hood. Does that answer your question, Gary?
Yes. I mean, so just what the last part, like, so because we have those neurons not being used, right? You're saying that the weight is still being adjusted, but what would be the outcome, right? Like, if I did use that neuron, it wouldn't utilize that weight, right? So then my output would be changed by not utilizing that weight.
Yes, and you're definitely right. We're getting into a little bit of what's going on under the hood there, and I don't want to get too far in depth there because there's some complex math that's utilizing like probability and statistics and all these other things to try to figure out how they talk to each level of neurons, that I myself would not be able to explain to you intelligently.
Okay, I got you. Appreciate it.
Of course. All right. Let me go ahead and stop the recording now. Hear me? Welcome back, everyone. Let's go ahead and continue on with our lecture. So currently we've been able to optimize our model a little bit. We can see that it is at 100 epochs. It's able to now have a loss of 64.9, which isn't very accurate. We've seen our loss kind of fluctuate over and over again, and we're going to actually talk about our loss and evaluating our loss here shortly. And we got our accuracy to go from the starting point, which was at 0.62%, to now climb all the way up to 0.68%. This is pretty great. Now, the next thing that we're going to be talking about is going to be how do we want to account for our model being overtrained, right? Now, when you do something like overtraining, I want everybody to think about overfitting, right? I'm feeding so much data into my model, where essentially my model has now become confused, right? My model has, rather than memorize pattern, started to memorize data. All right, I'm sure everybody has gone through the experience where you're trying to explain something to someone. You know, for example, I have this experience with my kid every now and then where I say something to her over and over again, and she's babbling it back to me. And then I say, okay, well, what did I just say? And all of a sudden she gives me the deers in the headlights look, right? Like, okay, perfect. So that's essentially what happens to my model when I do overfitting, right? It's repeating back to you the same exact information that you're trying to tell it. But the moment you ask the model, well, what is it that I'm actually telling you? The model doesn't know. It gives you the deers in the headlights look. So how do we stop that from happening, right? At some point, we have to analyze where our training is no longer productive. And we've taken a look at this loss item so far to be able to determine whether our training is productive or not. And we determined that our loss item looks something like this, right? Where the overall arching schema should continue to fall downward. But what about this spike here, right? How often should we allow our data to spike like this, right? Yeah, how often should I allow my data to spike? That's a spike in loss. I don't always want to allow for spikes in loss, because what if my loss, instead of following this downward slope, starts looking like this, kind of like a heartbeat, right? Where it's just continuously bouncing back and forth. What does that tell me as far as my optimizer goes? If I start seeing this within my loss, what does that mean in my optimizer? Anybody want to take a guess? Well, if I start seeing something like this, it means that my optimizer has now, rather than found the bottom, it's bouncing back and forth between my left and my right, and never actually finding the bottom. It just continues to bounce, right? Well, how do we account for this? Or how do we even identify this behavior? Well, we do that within the loss. And let me go ahead and start talking about what our goal here is, right? We want to stop the training loop. And let me go ahead and open up another parameter here. We call this applying an early stop. Things to consider, right? So overall goal, I want to stop the training loop if training is unproductive. All right. Now, how do I determine if training is unproductive? Right? How do I know that? How do I determine if my training is now unproductive? Let's hear it, Mo.
Maybe constant loss.
Yeah, so I want to keep track of the loss, right? So, determined by spikes in loss function. Okay. So there's my overall goal. I want to stop the training loop if it's unproductive. And I know it's unproductive if there's continuous spikes in my loss function. But now, which loss or when should loss be calculated to determine if it's unproductive? Anybody want to take a guess at that one? Well, so far, we've been taking a look at loss within the training loop. And we know that within the training loop, weights and biases are continuously being updated and they are continuously changing, right? And that does affect our loss functionality, right? The loss gives us our backward step. But I don't want to keep track of my loss per se before the backward step like I am here. Here I am keeping track of my loss before the backward step, right? I want to see what my loss looks like after the backward step, because I want to see those weights and biases already applied. So should look at it after the backward step. All right. And just like we talked about, when my model is in training mode, there's a lot of fluidity, right? Because we need the fluidity to actually be able to train our model better and ensure that our model is learning. But if I'm doing something like trying to calculate that my model is no longer making accurate predictions or learning in any sense, well, I would want to change this, right? I wouldn't want to just utilize my loss or calculate my loss after the backward step. I would also want it to happen where my model is in evaluation mode. So we don't take gradients and biases into account, right? So I'm essentially just trying to isolate this and make it as accurate as possible, where my loss is being calculated consistently after the backward step. So after I have tried to improve my weights and biases, and it's consistently happening when the when the model's weights and biases have been solidified and they are not taking into consideration any source of the any of the fluidity that we have within our model. For example, dropout layers. When your model is in evaluation mode, the dropout layers are no longer being utilized. Those dropout layers get thrown away when we put it in evaluation mode, because it knows that it's no longer trying to learn. Now it's trying to actually provide you a very straightforward answer. All right. So there's our models here. And this is how this is conceptually what we're going to try to apply, right? Now, there's a little bit more that goes into this. Let me go ahead and go back into editing. All right. Let's say we want to also account what is considered a negative spike. All right, we have to determine that, what actually considers a negative spike, and how many times will we allow a negative spike? Right? Because we don't want to kill it after the very first spike. For example, this here is also a spike, but we don't want to necessarily kill it there, right? So how many different spikes would we actually allow before killing the training iteration? And then how do we consider a negative spike? Well, as we saw here, 0.6 to 0.73, well, that's definitely a negative spike, right? But what about something, oh, we don't have a very good example here. Right? What if I had something where I had 0.61 and then in the next iteration I had 0.64? Right? Do I still want to consider that as a negative spike even though it's so minute? Well, let's break that down. Let's take a look at our training phase here. I'm gonna actually copy and paste this training phase and bring it down below so that we have it yet again. And now we're going to iterate this stopping functionality, right? I'm going to now create a function named calculate loss, or let's just call it EarlyStop. All right, so EarlyStop. Now this function is going to return a Boolean value. Well, just like we talked about before, there's a couple of arguments that I want this function to take in. All right. We said, hey, well, what is it that I'm going to consider a negative spike? And this is typically considered, or in, the actual terminology for it would be minimum delta, right? And we'll see that as the difference. If I were to talk about the difference between here, between this plateau, oh, excuse me, and this spike, what would be the difference in between those two? Well, that's what I reference to as minimum delta, which in turn will be a floating number, right? And then we have something where I also want to take into account how many of these negative spikes would I actually allow before I stop this this iteration. Well, this is called patience. And patience is typically an integer number, right? Where the standard is 5, where that's the default. So I'm going to pass in some default values here, where it could be 5. And the standard for patience would be 0.5. Or excuse me, for minimum delta would be 0.5. Oh, and I got that wrong. It's 0.01, right? So there's the minimum difference between the previous loss and the next loss should be between 0.01, and my patience should be of integer 5. It should only allow for anything above this difference to happen 5 times. All right. Does anyone have any questions as to why I have these parameters and how this is going to affect our model here shortly? All right, doesn't seem like there are any questions, so let's move forward into the implementation or the logic that's going to happen here. All right. Well, inside of this logic or this function, I would want to have something called best loss, right? Which we don't necessarily have already. So I'm going to say, hey, best loss. And I'm going to make this best loss be equal to none. And I'm actually going to pass this in as a parameter here. So I'm gonna have best loss, which will either be a float or none. Right? And there I see that my default value is none. So there you go, I have my best loss. The first thing I'm going to do when I pass this parameter in, or when I work this function, is I'm actually going to pass something called, I apologize everyone, I am going about this a little wrong here. No, this is work. This is funny. All right. So now I'm going to actually call this if best loss is none. So if best loss is none, I'm going to grab the new value here. So I'm going to call this validation loss, which will also be a floating number. And this one will actually be a parameter that we need. So I'm going to pass it in first. So if best loss is none, I'm going to grab the validation loss and set it to best loss. So there you go. I have my loss function there. I'm setting it to best loss. And my next question will be, well, if this isn't the case, then I want to know if val loss is greater than is greater than best loss minus the min delta. Right? So if my best loss was 0.4 and the next one or 0.004 and my next val loss was 0.003, then this wouldn't trigger. Right? Because I'm going to subtract that 0.1 first. All right. So then if it is greater, then I'm going to have something called a counter outside here. And as I'm building this function, I'm realizing that most of these here should be outside. And I apologize, everybody. I built this as a class. I'm trying to show us what it would look like as a function before we turn it into a class. So there you go. We have our patients, our min delta, et cetera, et cetera. All right. So if this is the case where my validation loss is greater than my best loss, then I would want to increase this counter. Say, hey, counter plus equals 1. Spelling something wrong here. I don't think so. All right. So now that I've increased my counter, I would also want to identify, hey, is my counter greater than or equal to my patients? Because if it is, then I want to kill this function, right? I want to return false. Or excuse me, I want to return true because I want to stop my function. Well, if this if statement is not triggered, where my best loss was not greater than best loss minus delta, then I want to have it where best loss is now equal to my validation loss. And I'm going to reset my counter to be equal to 0, right? So only if this spike happens 5 times, then I would kill my function. So let's break it down here. This is going to go through my training loop, right? As it goes through my training loop, Oh, let me make this into a solid line here. As it goes through my training loop, it identifies one spike. So it changes this logic, turns it back where my counter is 5. Or it drops a little. It's still where my counter, or excuse me, where my counter is 1. It's still not necessarily matching my best loss minus delta. So I'm going to add my counter again. Then it drops a little bit more. All right, well, just right now, it passed the value that it was before. So now my counter, rather than being at 2, is going to get reset to 0. And now my new best loss is located here. All right. So there's my function for early stopping. Well, how do I apply this into the training loop? Again, this is going to return a value, right? So I'm going to return here false. And I'm going to come down and apply this function into my training loop. Well, just like we talked about before, I don't want to apply this function into my training loop when my model is in training mode. And I don't want to apply this function into my training loop where it's taking into account the loss before the backward step. So within this for loop, or excuse me, right outside the for loop where I passed it through the training loader, I'm going to place my model into evaluation mode. And within evaluation mode, yeah, between evaluation mode, I'm going to go ahead and make something called validation loss. I'm going to make this equal to 0. Now, utilizing with torch no grad, because I don't want to actually apply any sort of gradients or fluidity or anything to my model. I want my model to be strict, right? So here, applying early stop evaluation, right? I want my model to be strict. Well, now I'm going to iterate through my testing features. So I'm going to say features and labels in my testing. And this is going to be testing loader, which looks like I named it test loader. And I'm going to grab my output. This should look very similar to what we've seen before, where we take in our features. But before, we were calculating our accuracy here. All right. I just did math.round, passed it into the accuracy. Well, in this case, I'm going to go ahead and calculate loss yet again, utilizing the same criterion, but now passing in the output and the labels. All right. This loss gets calculated to apply the backward step, whereas this loss gets calculated to evaluate if we want to have an early stop or not. All right. They're two completely different losses. All right. They happen at two different spots in the program. This happens before the backward step. And let me actually go up to our model here. All right. So this criterion with output and labels happens before the backward step, which is all of these green arrows here where we update our weights and biases. Whereas this criterion happens after the model has been updated. Right. And now I'm going to have my validation loss add the current loss dot item. And then outside of loops, I'm going to ask it, hey, is this valid? I want this validation loss to be divided and equal to the length of the test loader. Right, so this is going to be reset to 0. It's going to iterate through all these 32 features, add the loss item for all 32 samples or 16 samples, whatever we have defined inside of our test loader. And then from there, I just want the average of what it is. All right, so I'm dividing the sum of my val loss by the length of the test loader. Okay, finally, all I need to do is pass this validation loss into early stopping. So I'm going to pass it into the early stop and say, if val loss, I want you to print early stopping triggered. And let's see that I want it to also show me the number of epoch, right? And we're going to break the training loop. Otherwise, I just want my model to go back into training mode. And actually, we see that it's in training mode here at the beginning. All right, so that was quite a bit. Let me do a quick summary here over what we've done. We created this function. Well, first we determined the patience, how many times we would accept for a spike in the loss, which in this case was 5 times. We determined the minimum delta, which is the difference between those two spikes. Let me go back to our here. And let me see if I have a better way of depicting this. All right, the difference between those two spikes would be my minimum delta. I have my best loss, which as we know could either be none or it will be replaced. And I have a counter. Every time this function is called, I'm going to evaluate if the best loss is none. If it is none, meaning that it's the first time it's being called, I'm going to change it for the validation loss. If it is not none, meaning this is not the first time it's being called, I'm going to ask, hey, is the best loss minus delta, or is my validation loss greater than the best loss minus delta? If it is, then I need to increase my counter because that means that this is no longer productive. All right. And if my counter is greater than or equal to the patience, how many times I accept this spike, then I want to return true. Because that's what this function is supposed to return, right? It's supposed to return either true or false. Else, meaning that my validation loss is less than my best loss minus delta, I would reset my counter to 0 and reassign best loss to the current validation loss and return false. Within my training loop, the only thing I added is I put my model in evaluation mode. I then put my models or my validation loss to 0. I took away any sort of gradient or manipulation that's happening within the model. And then I iterated through the features and labels in my test loader, which is currently set to 16. I took the output and calculated the loss again. This loss is being calculated after the backward step, and it's also being calculated without considerations for dropout. And I add it to the validation loss. I don't want to run this early stop for every single sample. Instead, I want to run through the entire sample size of 32 batches or 16 batches and grab the average loss for all of those 16 batches. I will then pass that average loss into my function, which will return either true or false. True if we need to stop, and false if we are good to continue. If it returns true, it will break the epoch iteration. And if it is false, it will continue to print my number of epochs. All right, so now let's go ahead and actually take this off here so that we could see it. And our code is being formatted, I'm going to move this accuracy statement to the very bottom of my file. And I'm going to comment out my first training loop. All right, let's go ahead and restart our kernel. Let's clear our outputs. And let's execute all to ensure this is working correctly. All right, so it seems I got an error there. If early stop, break, it looks like the error is coming from early stop. Best loss cannot access local variable best loss where it is not associated with a value. Interesting. Let's see. Best loss is equal to val loss. Or none. I'm a little confused by this error here. Floating the counter. Okay, it's not associated with a value. Let me try to run this here. No, that's still giving me the same error. I'm not sure where this error is coming from. I don't want to keep you all here and watch me debug. So let's go ahead and take a 5-minute break real quick. I'll debug this and then we'll come back and continue. So currently it is 11 o'clock. Let's come back at 11:05 to continue the lecture. All right, it looks like the error I was getting is coming in from this global part. It wasn't able to identify that these were in fact not, it's a scoping issue essentially. I was calling some variables that belong to the global spectrum within this function, and for whatever reason I wasn't able to identify them unless they utilized the global keyword. But now I'm getting a little bit of a different type of misbehavior where it's stopping too soon. So I'm a little curious as to what's going on here. Let me go ahead and add a couple of print statement. To ensure that this is working properly. And let me take off this here. Okay, so we didn't see the first trigger. That's because it was none. It went through and identified 6.5. And it was triggered even though, oh, I see 0.64. So that would trigger it. And then 653 minus 64, that would trigger it again. 653, 64, okay, 652, 64, 649, 64. Okay, so we can see that it is in fact working correctly. Maybe my my min delta could be a little bit more friendly per se. All right, maybe rather than making it minus 0.01, which it looks like we are not essentially making that change there. All right, so there's the 0.64 and we are at 6.4 and we see 6.5. So maybe that 0.01 is a little too far or a little too much. Maybe what we want is something a little more friendlier. Maybe 0.005 might be more executable here. Okay, so now we could see it being ran a little better. It made it all the way to the 10th epoch. That's where it stopped at 0.005. And we can see my model accuracy has actually decreased quite a bit from applying this concept. All right, so let's try to make this 0.001. And let me restart my entire kernel and run the entire application now. All right, so it's going much better. Now it actually made it through 52 iterations, where at 0.001, it was not improving, right? So here we see we're looking for 618. Okay, so here's 618 again, and it looks like we have a couple of hidden print statements. Let me turn this into a scrollable element here. Okay, so 618, 618, 618, 618, 618. All right, so the one prior to 618 was 0.621, right? Our trigger says 0.621. Triggered it yet again, right? Where now our lowest point was 0.618. We lowered to 0.619, maintained 619, and now we started going upwards, right? So from 619, we went up to 620 and 622. So that kind of makes sense. We made it all the way to 52 epochs that go around. And now we're at 67% while preventing overfitting, right? There's a couple of things that I would like to do to experiment with my model to see if I could make it more accurate. For one, currently I'm going through batch sizes of 16. I'm going to change that to be 32 for batch sizes and then execute my model. It looks like my model finished training. This time early stopping happened a lot sooner than expected. It happened at 0.35 and it only shot me up to 66, right? So it looks like my lower number was more applicable here. If I go back to 16, restart my kernel, and then I run all. Well, now it's running a little better. All right, let's take a look down here. Actually, it's running worse. So now we're at 62. Yet again, we're back to where we started. All right. So I'm going to go ahead and put this back to 32. I'm going to go ahead and run my original training loop as well. And rather than going through 100 batches or 1,000 times, 100 times, I'm going to go through this 2,000 times in my training loop. And finally, I'll end with this last training of 100 epochs to identify if I have a loss. So I'm going to restart my kernel. I'm going to clear all my outputs. And finally, I'm going to run my model. And at this point, I do definitely expect to see an increase in accuracy. All right, we can see our epochs iterating through there. It looks like I took off my statement for 100, and now we're seeing it every 10th. So there we can see it slowly working its way down and then bouncing a little bit back and forth. Atom is trying to find its best way to get through it. While this is all compiling, let's do a quick review over everything we've done up to this point. All right. We have, in order to have better connections, we changed our layers so that instead of just funneling them in a triangle shape, we kind of mimicked this diamond where we opened up our neural networks by creating more neurons and then started the funneling process. Now, this gave us more connections, more weights and biases to work with so that our model can make more accurate predictions. From there, we added fluidity into our model by applying the Relu function, which would account for zeros and negative numbers. Right? It would either bump them or completely disregard them, depending on what their values were. And then we applied dropout layers to ensure that we were dropping layers when we didn't need, when we dropping layers at random every time there was a training iteration to ensure that there wasn't too much of an over reliance on one neural network and that our model was learning in a more complex manner. Right? Finally, we went to our early stopping where we identified, hey, well, we have these spikes in our loss and we don't necessarily want to allow these spikes in our loss to always happen. So we're going to have a minimum difference between these two. And when I train my loop, if I identify that there is more than 5 spikes, well, I want to kill my function. All right, so let's go through it now. It looks like we finished through the iteration of the big training loop of 2000 epochs. We then apply the early stop, which the early stop happened to be triggered at the 6th iteration. And now my model accuracy has fallen to 62%. So this could be for a number of factors. We did see it climb. Unfortunately, I am restarting my kernel and then executing my entire script over and over again, which throws a little bit of imbalance since essentially I'm creating a brand new weights and biases every single time I'm trying to execute this model, right? If I continue to run all again, we'll slowly see these increase back up to 0.68. But that is what we have as far as optimization. And just to ensure everybody doesn't get confused and that we don't think that our loss is, or our loss has been a result of our early stopping, I can go ahead and comment out the early stopping. Bring our loop here back down to 100. And if I clear our outputs and run it all again, okay, it's taking a minute to go through it. All right, it looks like at 60, it looks like we got 67% that time. So maybe there is something going on here within this early stopping that's throwing off our model just a bit. All right. Now, to end our lecture, we're going to actually turn this early stopping functionality into a class. All right, currently I have it within a function, which as we saw, turned into a pretty big mess. So now I'm going to take this early stopping function and I'm going to apply it into a class. So I'm going to name this class early stopping. And we're going to go through the process of building the same exact logic that we had here into a class. So class early stopping. This class will have an init method, which as we saw, my init method should allow for patience and minimum delta. Right, where I'll have some default values here, where my patience will be a 5, and my minimum delta would be of 0.001, which is what we set it to at the end. I will then do my whole assignment of self.patience is equal to patience, self.min delta is equal to min delta, Then I have my counter, which is 0. I have my best loss, which we will set to none this go around. And then I have my early stop, which is the property that I will utilize to evaluate if I should stop or not. Already set to false. I'm going to go ahead and utilize the call method here. So every time this class is called, it should be called with a validation loss being applied. I'm going to run the same logic that I did above, where I'm going to say where if self dot lost is none, or excuse me, is best loss is none, I want to say self dot best loss is equal to validation loss. And I forgot the if there. All right. Else if validation loss is greater than self dot best loss minus self dot min delta, then I want self dot counter to be aggregated, and I want to evaluate if self dot counter is greater than or equal to self dot patience. If so, then I want self dot early stop to be equal to true. Otherwise, I'm going to reset my counter. And I'm going to assign best lost to be validation loss. Right, so I took this entire logic that we had up here, and I just essentially turned it into a class. Right, if I execute this, we'll see that it works correctly. Well, now let's implement it into our loop down here. Right, we still have validation loss. I'm going to go ahead and bring in early stop, and I'm going to make that equal to an early stop instance. Excuse me, that's going to cause an error. I'm going to turn that into an early stop instance. And down below, oh, no, everything looks exactly the same. All right, I pass in the parameter. Cool. Yeah. So now down below, this will work off of that one class rather than working off of the function. And let me ensure that I am not missing any sort of syntax there. I have my model.eval, my validation loss, Toshinograd. Okay, my output just takes in labels, validation loss, item. All right, go ahead and restart my kernel here. And let me run all. Okay, so it looks like we have an issue here with, oh, never mind, we don't have an issue. It looks like my validation loss, turning it into a class worked a lot better because now I was actually able to iterate through all 100 epochs there. And my accuracy, for some reason, when I apply my early stopping, really false. I need to figure out what exactly is causing that behavior. Let me bring that up here as well. All right, creates my model, goes through this binary function, which I'll go through it 100 times. Great, calculates my accuracy. So here my accuracy is at 67%. But after applying the early loss or the early stopping function, it looks like it falls considerably Oh no, it's still 67%. All right, maybe there was some sort of weird behavior happening in the background there. But there you go. That's early stopping in a nutshell. It's to identify the loss or at which point training has become unproductive, so that our model is no longer just iterating through the same information and getting confused with overfitting. All right, I know that was a lot. There was quite a bit of debugging on my part, which likely added to some confusion, which I apologize. Let me do a quick recap here over the class, and then we'll open up for questions. So here's the early stopping functionality. We have all of these attributes being set to self. This should be regular OOP. This is the call dunder method, which we haven't seen yet. It's something you give to a class when you want to execute this as a function, right? So I'm essentially executing this class as a function, or if I'm going to execute it, here's the call method. What it would take in, it takes in validation loss. It would evaluate if this is the first time that this is being called. If so, it would set best loss as the validation loss. If it is not the first time it is being called, it's going to subtract best loss from min delta and ask if the validation loss is greater than that, right? If it is greater than that, then the counter would take into place where we would increase our counter by 1. If our counter then was greater than or equal than the patience that we've provided, which in this case was 5, then we would stop our training loop. Otherwise, we would continue by setting our counter back to 0 and then setting the best loss to the new validation loss. Right. Down below, still have a training loop, which we should be pretty familiar with. Don't need these 2 lines of code because we already have them. Here we're going to go through our model. We're going to train it to the best of our ability. We're going to utilize with torch no grad only for this portion of our program, where I'm passing in my features and labels to my of my test loader to my model, so that I can grab the output or prediction of my model, calculate the loss after the backward step and without any implementation of the fluidity that we applied to our model, and then calculate the validation loss by adding the sum of that entire 32 set of that entire set of 32 batches and dividing it by the length of 32 batches. So I'm having an average here. Once I have that average, I'm going to pass it into validation loss. And let me go ahead and run this here. This could be the issue actually, where it was able to make it through. So let's say stop early stop. I'm gonna call validation loss. Then I could say early stop dot, and I believe we call this, let me go back to my class here. We called it early stop dot early stop. Nice. Because I need to make sure that I grab that attribute. So let me go ahead and execute this one last time. There's a little bit of issue in my code. So I call the function. This doesn't return anything. It only continues to speak to the attributes in my class. Okay, so there we saw the early stop was triggered at the 8th step. And my accuracy is at 6.9. The first time I ran it without the early stop, my accuracy did stop at 6.935. I tried to train it again, and it said, hey, this has become a productive, but we did improve all the way up to 6.96. All right. At this point, does anyone have any questions over any of the material that we covered today as far as optimization, both in the training loop and our model itself? Let's hear it, Momo.
Yeah, I'm just wondering why the early sub function, why you made it class after that? Why you turn it into class instead of function? Why you
Yeah.
didn't just use it as a function?
That's a great question. So why utilize it as a function rather than utilizing it as a class? Well, one, in Python, right? Or Python is an object-oriented, well, it's not an object-oriented programming, but it can be utilized as both a functional-based programming and object-oriented programming, right? As you'll see in your career as you continue to utilize Python, most of Python code is utilized in classes or written in classes. When we go into Django, everything is going to be in classes, and we should become accustomed to writing everything in classes. It also brings in some extra flexibility. As you saw when I had it as a function, I ran into the unexpected error where it wasn't able to identify patience, best loss, and min delta. And I had to utilize this global keyword, right? Well, the entire error happened because it wasn't a class, right? By turning it into a class, well, now my class has its own self-contained attributes. I could have separate instances of the early stopping class running at once. Whereas if I made it into a function, I could only run the early stop once because it's interacting with one single patience, one single min delta, best loss, and counter, right? Whereas every time I make an instance of this class, each instance has its own patience and minimum delta. So I can make multiples of this class, right? I could have early stop. Maybe instead of utilizing early stop, I want to utilize early stop with more patience. And I say, well, this is going to be the early stopping class, but I want patience rather than being 5, be equal to 10. All right. And all I need to do is change this early stop to say with more patience. And when I execute this block of code now, well, now it has more patience. It can wait. And we saw that it made it through the 6th iteration, which was where we stopped before. It made it all the way to 21. I increased its patience to be 10. And it didn't really help my model. Oh, I didn't run this yet. Let me run that. Yeah, and it didn't really help my model become more accurate. In any case, by giving it more patience, I ended up hurting my model because now my model is at 6.9 and where it was at 6.96 before. Does that make sense, Momo? It's just a
Yes,
simple.
makes sense. Yeah,
Okay, awesome. Any
that's
other
very good
questions?
answer. Yeah, thank you.
Of course. Let's hear it, Gary.
Your minimal delta, uh,
You're muted. All I heard was your minimum delta.
I was saying your for your minimal delta, it looks like it's a value that you pick. Should that be relative to the data set that you're working with? Like, would that number adjust based on, how much the range of data that you have essentially, or like what parameters you're trying to adjust to? So like you would increase the delta if you had a wider loss, right? Or like a point outside of your mean data set.
Not necessarily. So your data is already standardized and scaled. Your min delta, it's by default, you should always go with 0.01. I believe that's the default that you'll see in documentation. Um, and at that point, it kind of just turns into the experimenting process, right? If, hey, is this really what I want? I really want 0.01. Maybe 0.01 is what you want, but maybe you want to change your patience to instead of being 5, being 10. It kind of just, you got to start playing with it to see what would allow your model to learn best. Um, does that answer your question?
Yeah, I guess I was just looking to see if there was a more accurate way of
Like,
picking that. Guessing
right, like a direct correlation.
exactly.
Right. Yeah. All right. Any other questions? Okay. It doesn't look like there are any other questions. I'm gonna go ahead and stop the recording now.